Hi, I'm Rohit Gandikota, and I'll be talking about our work SliderSpace, decomposing the visual capabilities of diffusion models. This work is done in collaboration with Northeastern University and Adobe Research. Taking a step back, state-of-the-art diffusion models always keep getting more and more powerful in terms of their capabilities and their realism, with their ability to follow the text much better over time. More interestingly, when you provide a prompt like picture of a toy to a diffusion model, it can generate theoretically infinite variations of this prompt depending on what is the initial noise seed that you provide. In this project, we specifically asked this question: how is the model generating so many diverse images? Can we look inside this model and capture the knowledge it uses for diverse generations? Perhaps the model uses concepts like Lego, plush, and knit, and whenever it's generating a single image, it probably uses this hidden structure and weights them differently while generating an image. Essentially, if we capture this hidden representation structure and be able to control it, we are giving the users of these models to control the model's internal knowledge structure. Let's get into how SliderSpace works. We begin by generating multiple images for the prompt that the user provides, for instance, mango art. And we extract semantic features from each of these images. A semantic feature can be output of semantic models like CLIP, DynoV2, FaceNet. Then we decompose these semantic features using PCA. And each of these directions explain the most variations that this distribution represents. We then learn sliders for each of the PCA component that we extracted. So every slider, once attached, should change the output of the diffusion model along these semantic features like clip across these PCA directions that we extracted. And the gradients flow through this clip model and diffusion model and updates the weights of the sliders. In summary, when a user provides a single prompt, SliderSpace extracts sliders that would explain the variations or the diversity that a diffusion model is capable of generating under the assumption of drawing multiple seed images. Every slider tries to mimic the top variation direction in the semantic knowledge space of the diffusion model. Once generating, what we find is that these directions are unsupervisedly discovered. So to label them, we apply these directions post-discovery and label them using automatic tools like a VLM model like Claude 3.5 Solve. Here are some interesting directions we found for the concept monster and car. As you can see, each slider has a very consistent semantic effect on the outputs. And when these images are passed through a vision language model, it is labeled appropriately. Since these are sliders, you can control the effect that it has in its output images just by controlling the magnitude at which we apply these sliders to the model's weights. You can find more of these directions in our website, given below. Another application that we are really interested in is exploring the capabilities of an unknown model. When a new model comes out, what's the usual way that the community explores this model? Well, one of the examples is these efforts led by Parrot Zone team. When Stable Diffusion 1.4 was released, Parrot Zone team started manually searching for all the artist styles that a Stable Diffusion model can mimic. They collected a huge list of artists that were ever to exist. and manually put their names and prompted the stable diffusion model, generated the output, and compared these models manually with the real art created by the artists. Through that efforts, they discovered more than 8,000 artistic styles inside stable diffusion. And as you can imagine, this is a very intensive task, which takes a lot of time and humans in the loop. We pose this question, can we use SliderSpace for helping users explore these unknown capabilities of a model? We start by decomposing the concept art style using SliderSpace, and we found a lot of interesting new directions or new art styles inside Stable Diffusion XL. Essentially, each of these directions are the basis concepts or features that Stable Diffusion XL uses to encode the concept of art. Now, once we give these capabilities to the users, users can create different arts by composing these SliderSpace decomposed sliders with different weights. Luckily, we have also the real true ground truth that SDXL can mimic, thanks to Parrot Zone team's efforts. We now compare, does SliderSpace really extract the true distribution of what a model is capable of? So we compare SliderSpace generated images with this real artist names prompted generated images and see how close these two distributions are. We also have multiple baselines. For instance, when you simply generate artwork in the style of a famous artist 10,000 times with a diffusion model, most of the times it's a similar looking artistic style. It's not very diverse, and it doesn't really match the real artist distribution. As you can see with the FIDs, it's much higher. The lower the FID, the closer the distribution is. You can also use powerful baselines like asking a language model like GPT-5 to generate a list of art styles and manually prompting the diffusion model with these artistic styles that LLM has provided. This closes the gap quite a bit compared to generic prompts, but still has a higher FID of 38. We also compare it against concept sliders, where LLM-generated styles are manually trained using concept sliders, and we randomly compose different concept sliders to generate a distribution which also doesn't quite get close to the real artist that the SDXL is capable of drawing. Finally, we compare SliderSpace generated images. Essentially, during inference, we simply ask art in the style of a famous artist. But similar to the generic prompts, in addition to that, we also attach random sliders that SliderSpace has generated or extracted. And we immediately find that this distribution is much closer to the true ground truth that SDXL can mimic. In essence, SliderSpace represents more of the true distribution of what a model is capable of. We also found that SliderSpace trained on one concept can be transferred to several other concepts. For example, look at these sliders for the concept person. We find many interesting ones like long hair, wrinkled, innocent eyes, hoodies. These sliders can be directly transferred to a different inference prompt like police, athlete, which are not very surprising as these are also person-related concepts. Interestingly, these also transfer to out-of-distribution concepts like a dog. You can see that the dog gets glasses with wrinkled hair and a plus-size dog. SliderSpace can be transferred from one concept, extracted for one concept, and can be applied to any other concept during inference. We also try to capture all of the variations inside a diffusion model. What do we mean by this is, well, a base diffusion model is capable of drawing beautiful images, but is usually slow due to the number of time steps it requires. And then distillation methods essentially try to reduce this time by making them super fast and yet generating nice images. However, they lack the sample diversity when drawing these images. So what we do is we extract slider space for diverse prompts like Coco 10K, and we look at these different sliders that are extracted and the variance that these sliders explain in the distribution. Now, during inference, we sample the least variation explaining directions much higher than the ones that explains more variation. Implicitly, this improves the diversity generated by these distilled models. We are artificially increasing the basis directions that the model uses when generating images. We find that these directions actually improve the distilled model's diversity and brings it much closer to the base model. And a bonus is these are generic sliders. You don't have to train them for any other concept. You can just take these sliders and always use them for any inference for your distilled models. Thank you for listening to the talk. And for more details and code, please visit our project page.